Hi friends, this is the sixth lecture in the lecture series for the preparation of GAT Mechanical Engineering. Today we will be dealing with a concept called critical radius of insulation. Critical radius of insulation. For that case we have to consider some pipe through which some fluid is flowing. So suppose this is the pipe which is denoted by the color violet, and this is the fluid that is flowing through this pipe, and it is having the heat transfer coefficient HO, and this is the pipe material which is having the thermal conductivity K pipe, and this is the insulation material that is around this particular pipe. Let's suppose we are considering the insulation material is around the pipe and which is having the thermal conductivity K insulation, and also suppose let some fluid is flowing outside this pipe and which is having the heat transfer coefficient HO, and it is at temperature T infinity. So for this pipe we are having internal radius Ri and this external radius Ro and the radius of insulation material which is R. So if we convert this to a resistance circuit, we can draw like this. Okay, so this is R1 which is due to the fluid that is flowing inside the pipe. This is R2 which is due to the pipe itself. This is R3 which is due to the insulator material, and this is R4 which is due to the fluid that is flowing outside the pipe. So let's find the equivalent thermal resistance. That is, to determine the equivalent thermal resistance we have to first find the individual resistances. So R1 is nothing but a convective thermal resistance which can be written as 1 by Hi into Ai, which is equal to 1 by Hi into 2 pi Ri into L. So R2 is due to the pipe, so R2 will be equal to ln Ro minus ln Ri by 2 pi K pipe into L. L is the length that is perpendicular to this page, and R3 is the conductive resistance which is due to the insulation material, which will be equal to ln R minus ln Ro by 2 pi K insulation into L. So next the R4 which is nothing but a convective thermal resistance which is represented by 1 by Ho 2 pi R into L. So let's write the equivalent thermal resistance. RTH equivalent will be equal to R1 plus R2 plus R3 plus R4, and this is written like this since we are connected all the resistance in series combination. And please go to the previous lecture for better clarifications. So expanding this, we can write 1 by Hi 2 pi Ri into L plus ln Ro minus ln Ri by 2 pi K pipe into L plus ln R minus ln Ro by 2 pi K insulation into L plus 1 by Ho 2 pi R into L. So in these cases, or in this equation, we can find that these last two terms is only have the radius of insulation, that is R. So if we increase the radius of insulation as R increases, what happens is that the decrement in R4 is greater than increment in R3. That is, decrease in R4 is greater than increase in R3. In effect, what happens is that heat transfer will increase. So as the radius of insulation increases, instead of reducing the heat loss, it will cause the increment in heat loss. But this increment is up to a certain radius r, which let's suppose let's write as r star for this, for simplicity as of now. If we increase the radius beyond r star, and this radius is the radius of insulation beyond this particular r star, what happens is that increment in R3 will be greater than decrement in R4. That is, R3 increase will be greater than R4 decrease. So what happens? The resistance, equivalent resistance will increase, which will cause heat transfer to get reduced. Okay. So this particular radius r equal to r star at RTH equivalent is minimum, or heat transfer is maximum, is called the critical radius of insulation. Okay. So to find this critical radius of insulation value, we have to derivate this RTH equivalent with respect to R and equate this to 0. And doing this, we will be getting 0 plus 0 plus 1 by R by 2 pi K insulation into L minus 1 by H O 2 pi R square into L. Cancelling 2 pi and L in both sides, which will be equal to 0. And we can write 1 by K insulation into R is equal to 1 by R square into HO. So cancelling this R and this R, we can write this R is equal to K insulation by HO. So this R is nothing but the critical radius of insulation for cylinders. Okay. So let's suppose we want to decrease the heat transfer loss. To reduce heat transfer, we can provide insulation at outside and inside. Let's suppose we are providing the insulation outside the insulation can be provided at outside and inside. Let's suppose the outside case. If we are providing insulation outside the pipe, what happens, and here is that this is the radius R and this is the Q dot and this is R, and the heat transfer will be following this curve. Okay. So, and this is the initial radius of, and this RO is the radius of our pipe, and this is the initial heat transfer. We can see that the heat transfer will be maximum at some point, and which is denoted as R star, which is the critical radius of insulation. And we can see some point over here, and which is the same heat transfer, that is without the insulation case, and this is represented as letter R plus, and this can be determined by equating heat transfer with and without insulation. Okay. So to reduce the heat transfer, we have to provide the insulation outside the pipe at a radius, use a radius R which is greater than R plus value, then only this insulation will be effective. Insulation effective. Okay, so if you are providing insulation in the inside of the pipe, we can draw a similar curve like this. This is radius R and this is the heat transfer, and this is the heat transfer curve, and this is the point of maximum heat transfer, and this is the radius of pipe, and we are providing some radius which is less than the radius of the pipe, and this will be the point for that particular radius, and this will always be less than the heat transfer that is without insulation. So in this case, as radius is less than radius of the pipe, then the heat transfer will be always minimum, especially less than heat transfer without insulation. Okay, so if you want to enhance the heat transfer, we have to keep the radius of insulation